Okay. Hello, hello, hello. Star Wars, Star Wars, Star Wars. Okay, there we go. People are going to wonder about this. They are, yeah. That's better. Kind of. Sort of. Can we continue? Yeah. Let's do that. Here's example 2, everybody. So example 2. The mean score on what? On the SAT, math reasoning exam was what? 560. Thank you. A test preparation company states that the mean score of students who take its course is what?
Higher.
Higher. So is that going to be not equal to, less than, or greater than?
Greater than.
Good. So now you know what the null and alternative are. Good. So that's a little better? Starting to get the idea? Getting used to the language a little bit?
Yes.
So what we want to find is what? Determine the null and the alternative hypothesis is correct. Good. So does that make sense for the null?
Yes.
That the null, H0, is that the population mean is equal to what? 516. Does that make sense?
Mm-hmm.
We just started. No problem. What would I write for the alternative? High, as Martha told us, or HI, or really H1, right?
H1.
Yeah. Does that make sense to you? And what kind of, is this right-tailed, left-tailed, or two-tailed? Right-tailed because it's what?
Greater than.
Yeah. I mean, it doesn't say that, but just to get you in the habit of thinking that way, because later it's going to be important, that habit is kind of a good thing. Any questions?
What tail is it?
Right tail. Basically, the direction of the inequality, where it points, tells you the type of test you're going to use. So if it points to the right, it's right tail. If it points to the left, it's left tail. If it's not equal to, it's probably pointing to both. That's why it's two-tailed. Yes. Yeah, it is. It is what we did before. Like a lot of what we did before. Any questions? Any questions, everybody? We know when you're ready. I know they didn't cover this in 137.
No.
For a fact. No. No, they don't. No, I think you just went up to chapter probability.
Stuff that they covered that is not in the class.
Oh, the nonlinear stuff. Oh, yeah. Yeah, we don't do that at all. Yeah, because I'm teaching that class over statistics.
That one doesn't have a book, so it's like.
No, it doesn't have a book. It's actually, but that, yeah, we're going to be starting a new class. It's called Math 137. The prereqs are you only have to have 112.
115.
Is it 115? I don't know. I heard 112 from somebody. Maybe it's. I think I don't know. I heard 112, but I could be wrong. And either way, it's kind of an algebra-like class. It's really, it's a good intro to statistics. So we cover like the first 5 chapters of this book.
Oh, the same book we have right now?
Well, it's similar, but it's called OLI by Carnegie Mellon.
It's called what?
OLI, Open Learning Initiative.
So you have to take 115, or you have to take in 115.
And pass it, yeah. Pass it with a C, yep.
Open
Learning Initiative. It's free. But it's not an easy book. It's even hard. It isn't. It's even hard for statisticians to know. It's hard even for us. It's not easy book.
Print pages out from there when you
Or read it.
for your notes.
Oh yeah, or read it. Yeah, I would read it a lot. We have activities. They have online activities that you do, which are really useful, I think. So
And
it's a
you
neat class.
can email the professor like right at the end of that activity.
That's right. I get a lot of emails from students. Good for you.
Is this in the fall?
Yeah, starting fall. They've been teaching it for the last year with full-time instructors. I'm the first non-full-time instructor they're allowed to teach it.
Because it was a demand class.
It's a demand class. And also because I've taught it before, and I don't know if you know who Claudia Reyes is. Professor Reyes? You ever heard of her? What's that? No, it's okay. She's a really good professor here too. She also teaches at COC and here, and she's going to be teaching it too. So both of us are the guinea pigs. We're going to be teaching it. We're the new adjuncts. So they're adding an extra class. We're going to have 3 of them. Eventually, we want to make it bigger. And I told your Jennifer, right? Jennifer, I told her comments from my chair, and she liked it. She thanked you. She thanked you for your comments.
Wonderful professor. So yes, you know, she's the vice chair for
And I told the chair about it, and she was very happy that you said that.
Yeah.
So thanks. Thanks for the feedback. Now, if we want to, let's say if we actually reject the null hypothesis, now we want to write the conclusion. So there is enough evidence, or there is not. What would you say?
Would it be like a type 2?
Not.
Wouldn't be, that's the type of error. Now we're actually trying to figure out, kind of, but actually we're actually trying to write the conclusion of our study. So we either have there is or there is not. So we're rejecting or we're not rejecting here.
We're not rejecting.
We're not rejecting. So there is. So we say there is or is not. There is not.
Well, it says it's there, not be rejected. Is that the clue to that?
That's the clue. Yes, that is the clue to it.
Right.
When you're not rejecting. So it says, if the sample data indicates that the null hypothesis should not be rejected, okay?
There is not enough.
Then you say there is not enough evidence to support the mean score of the reading exam to be what? Higher than 516.
And the other one was?
There is evidence to support the claim that the reasoning of the exam is what? Higher than 516. So all you do, so when you don't reject, you just remove the word what? Not.
Yeah.
I mean, when you're rejecting, in other words, when you're rejecting the null hypothesis, you remove the word not. When you're not rejecting, you include the word what? Not. So let me say that again. So when you reject the null hypothesis, you exclude the word not. But when you don't reject the null hypothesis, you include the word not. That's right.
So when you're rejecting it, sorry.
No. When you reject the null hypothesis,
Yes.
you say there is sufficient evidence.
Okay.
You omit the word not. But when you don't, you include the word what? Not. See what I'm saying? No.
Mr. Addis, can you repeat that again, please?
When you reject the null hypothesis, you include the word, you omit the word not. Omit. That means remove the word not. You just write there is sufficient evidence.
Okay.
When you do not reject the null hypothesis, you include this word, not.
So it's either going to reject it or not reject it.
Yes.
But it's never accepted.
Right. You never say accept because.
It's reject or not reject.
And does everybody want to know the reason why you don't want to say that? Why you don't want to say accept? Because this is one experiment. You do another experiment, and it's possible you could what? Reject the null hypothesis. Maybe you haven't picked the right experiment yet.
Okay.
So that's why we don't want to say accept.
So when they do accept it, is that when it becomes a theorem? Or whatever?
Yeah. Or an idea. Basically, you're trying to reject claims.
Right.
Yeah. Then that new idea, like if we think it's higher, then we want to say how much higher.
Right.
Well, maybe it's a new value, and that could be the new hypothesized value. And then we test it again.
Mm-hmm.
So it's a never-ending process.
Yeah.
It's kind of neat, though.
Yeah. It goes on and on.
It does. Good question, by the way. Thank you, Lauren, by the way. You ask good questions. Keep it up. Made me think. Let's look at C. Now, here's this. Now, this is a different question than part B. And Razan, do you see how this question is a little different? It's more like the first question you were thinking about.
Right.
The B says just write the conclusion. In other words, there's no error of type 1 or type 2. Here we actually have, what if we were to write a type 1 or type 2 error? In other words, suppose in fact the mean score of the students taking the preparatory course is 522. So that's contrary to what we did. Because what we did in part B is we didn't reject the null hypothesis. In other words, we didn't find any evidence to think that the score was what? Bigger than 516. But now let's say we do find evidence. Okay?
Would it be type 1 then?
It would be type 1 or type 2. So, what would be type 1? What did you say? It was type what? It was type 2. It's type 2. Let's figure out why.
I would have thought it was 1.
Let's see. We can have debate. Debate's good. It's type 2. So let's see why. Okay. Type 2 means that you, remember, initially we didn't reject the null hypothesis, right? Right? Okay. Now we found evidence that what we think actually contradicts what we just did. So now we are rejecting what? The null hypothesis, even though the null hypothesis was what? Now is not, well, let me back up a minute. We what? Didn't reject the null hypothesis. Do you guys agree?
Right.
You didn't reject it. That's part B. You with me?
Mm-hmm.
But now, so when we didn't reject it, we assumed it was what? True. The null hypothesis. But now, we actually have evidence that it's false. So we didn't reject the null hypothesis when the null hypothesis is what? False now. Why is it false? Because the value of the exam is what? 522. So that contradicts it being 516. So in other words, we're not rejecting the null hypothesis when it's false. So that's exactly what Martha just said.
I guess so.
So that's why it's what? A type 2.
Type 1.
Okay? Any questions on that?
You had mentioned earlier that the type 2 we can control and the beta or 2 error,
Yes.
can we not control that?
Well, if we control it, that means the other one, the type 2 error, is going to be bigger. It's going to be, in other words, if we make the type 1 error as small as possible, it's going to make the type 2 error bigger. It's going to be a larger value. In other words, we're going to actually basically set free guilty people. More of them.
You know how we are able to see the confidence interval on your normal distribution?
Yeah.
Can this also be seen on a normal distribution?
Yeah, it usually is, yes. And that's coming up.
I'm still having a hard time seeing it.
Yeah, it's coming up. We're going to show you some pictures. I know this is a little abstract, but it's coming up really soon, okay? I'm sorry, it's not, right now, it wouldn't really be relevant to kind of talk about it now, but it will come up, okay? And I'll put it in context for you, okay? I'm sorry about that. And the next statement says, if we tested this hypothesis at an alpha level of 0.01 or 1%, what is the probability of committing a type 1 error? Well, that's just that number, 0.01. Because that when alpha equals 1, that's the probability of making a type 1 error. That's what it is. In other words, this is what we call the level of significance, and what that is it's the probability of making a type 1 error. And in this case, it's about 1%. Okay? Any questions? How are we doing time? Not bad. Any questions on that? Now, let's see if you guys know, okay, from what I said previously. So let's read D carefully. You guys want to read together?
Yeah.
Let's read together. If we
wanted
go ahead. If we wanted to decrease the probability of making a type 2 error, would we need to increase or decrease the level of significance? Which one do you think it is? How many people vote for increase? Increase. How many people vote for increase?
Oh, wait, say it again.
How many people vote for increase the level of significance?
Which level?
Well, okay, so remember, type 2 error is beta. Type 1 is, so okay, how many people say increase? So you say increase? How many else will say increase? 3 of you, 4 of you? That's all? How many say decrease? How many are hedging and just want to hear the answer? Remember, you can always say the hedging factor.
Wouldn't it be vice versa?
No, it wouldn't be.
I'll take anything.
No, you don't want to take anything. Remember what happens. If you make this smaller, you make this larger. So its increase is correct. That's why we can't make them both what? As small as we can. That's the problem. We can't. So if we increase alpha, we decrease beta. This is type 1. So if we increase the type 1 error, we decrease the type 2 error. And vice versa. If we increase the type 1 error, if we decrease the type 1 error, we increase the type 2 error. So let me say that one more time. If we increase the type 1 error, that's what alpha is, okay? We decrease the type
Beta.
which is the type 2 error. Now let's say we decrease the type 1 error. What are we going to do to the type 2 error?
Increase.
You got it.
But level of significance in this context meant 522, right? Or what number?
Nope, not 522. That's the value of the parameter.
Oh.
That's the value of the mean. Level of significance is alpha.
Oh, okay.
That makes more sense, right?
Because I was going to figure out what that means.
Because think about it, this is a probability. And actually, that's kind of a good point.
Oh, yeah.
This is a probability. Can you ever have a probability bigger than 1?
No.
Never. So that's a dead giveaway.
Oh, yeah.
You can never have a probability bigger than 1. Alpha is a so alpha and beta are both probabilities. These never can ever be what? Bigger than 1. Ever.
Or
Ever.
less than 0.
Or less than 0 is correct. Very good. You guys see that? That's really important.
So were we correct in saying increase?
You were correct, yeah. The 4 of you who said increase is correct. Yeah.
This is just the opposite. It's just the opposite, right?
It's just the opposite of what, yeah. If one goes up, the other one goes down, and vice versa. It's like a seesaw.
So it's like a level, pretty much.
Wait, is it like a level, or is it like a seesaw?
Like a seesaw.
Is it a seesaw or a level? Is it a level seesaw?
It's a one out of 3.
Is it one of the two?
It's both at the same time.
Is it both at the same time? That's what I'm trying to tell you? Yeah. Well, it's either one or the, actually that's what Rosanna Downey used to say.
Yeah.
It's either one or the other. She used to say that.
Oh, from Saturday Night
Night Live, yeah. That's how Rosanna taught me how to say her name. It's like, remember Saturday Night Live?
Yeah. You kept calling me Roxana.
Yeah, at first I called you Roxanne. That's what I did.
He was like, uh-oh.
Now, therefore, if you increase the level of significance in order to decrease the probability of a type 2 error, that's what you do. And again, which one is which? In our case, we're playing with alpha. We're manipulating the level of significance. In theory or in practice, you got to pick which one it is, and it depends on the problem. Depends on what you're looking at. Again, you might want to make the type 2 error smaller or the type 1 error smaller. It depends on what you're looking at. And it's all problem dependent. But for us, we don't have to pick it. I'm actually manipulating it for you. Okay? But in practice, no, you have to pick it as an experiment. That's what makes it really hard.
Yeah, because you don't know what to choose. Do you
Right.
want a false positive or a false negative?
Yeah, it depends on what you want to live with. If you want to, for example, if you want to have people test positive for, let's say, performance-enhancing drugs, when in fact they haven't taken them, and you can live with a lot of people doing that, okay. Right? In other words, you're convicting innocent people, okay. But on the other hand, if you're letting people go who are maybe, let's say, guilty, like maybe they take a lie detector test and they say that they're not terrorists, and in fact they are terrorists, and you're letting them go, and that happens more often, that would probably be a bad thing to happen, wouldn't it? So you'd want to make that probability of releasing guilty people very low. right? Because you don't want people to commit crimes you set them free and they're going to commit crimes. You don't want them to do that, like a terrorist or something like that.
But then that one innocent people, one innocent.
Well, you got to make a trade-off. Either you convict innocent people, or you set free guilty people, and you got to make a trade-off.
It's only the innocent. I think we
You know what? It depends on the problem. I can't tell you.
because it's not gonna.
The best of the two evils.
Yes, you got to look at each one and see which is a policy as like a political policy you want to live with.
Take it to the extreme, like the absolute extreme, not everyone.
Well, I mean that is an extreme. I mean that is one way. You lock everybody up, but then what do? You're convincing what? Innocent people. That's the problem. But that's true. But then on the other hand, if the other extreme, you set free people, you're going to have people still committing crime.
But because people will be at prison.
Right. So I mean, yeah. So actually, what you're saying is kind of what the criminal justice system does. They err on the side of what? Of convicting people. Which is probably safer for society in the long run. Whether it's moral, that's another story. Here's another one. So let's look at the CDC. Finally something that's about headaches. Okay? Migraine ones, in fact. So according to the Centers for Disease Control, very famous place, 15.2% of adults experience migraine headaches. Okay? Stress is a major contributor to the frequency and intensity of headaches. I have to believe it. A massage therapist feels that she has a technique that can reduce the frequency and intensity of what? Migraine headaches.
Right.
Let's figure out the null and the alternative hypothesis.
Right.
Well, now, do we have a percent or do we have a number?
A number.
We have a percent.
Actually, we have a percent.
That's a proportion.
So it's a
I didn't
proportion.
finish my sentence.
Well, okay.
That would be 0.150.
You have a percent.
So it'd be 0.152.
That's it? No, okay.
So in this case, your P, now notice your parameter changed, didn't it?
Yeah.
You're not using U anymore, are you?
No.
You're using P.
It doesn't tell you the mean up there.
It doesn't tell you the mean. That's a dead giveaway. Also, again, if you're given a percentage, just like when we do confidence intervals, when you're given a percentage, that tells you that you're estimating P instead of mu. Same thing here. If you're given a percentage, you're estimating P. Here, we're hypothesis testing with what? P.
P, which is 0.152.
Yes. For the hypothesized value, yes. The alternative would be that it's smaller. Do you agree?
Yes.
Yes.
Why? Because it says decreased. Or reduced, excuse me, reduced in this case.
Where does it say that?
Reduce.
Oh, I see, okay.
Okay? That's all you have to do for part A. You just state the what? Hypotheses. All you're doing. Okay?
In words, how would those phrase the first one?
You're saying the null hypothesis says that there's no difference between P and 0.152. Here this says there is a difference. And in fact, that the difference between these is smaller than 0. Because if you were to subtract this number from both sides, that would be that P minus 0.152 would be less than 0. You guys see what I mean? In other words, can I show you guys what I just said?
Yeah.
Another way to say this, the alternative, is to do this. You see what I did? I subtracted what? 0.152 from both sides. And that makes that 0, doesn't it? And that makes this what? It says the difference between these two is less than 0. If it was greater than, it would be greater than 0.
What did you just say?
I said that the difference between the parameters, the population proportion, and its value is less than 0.
But the other one,
The other direction, if this was greater than, for example, that, you would say that the difference between the population proportion and its value is greater than 0.
Okay.
All right? You did, Jim?
I got the one at top.
This is if we were to do it alternatively. If we change the alternative to greater than, that's how we write it. That's another way to interpret it. So these statements that I'm writing here, there are other ways of writing the alternative hypothesis. They're the same thing. This and this are what? Equal. Do you agree?
Yes.
Do you see how this is the same thing as this? And what? This is the same thing as this.
Yes.
So just two different ways of writing the same thing. Just doing a little algebra. Okay? Yeah. No? Okay. Oh, okay. No problem, I guess. Let's look at, that's not a good thing. So let's read part B. Example of what? 500 American adults who participate in the massage therapist program results in data that indicate the non-hypothesis should be what? Rejected. Provide a statement that supports the massage therapist program. You would say there is or there is not?
There is.
There is. Because you're rejecting it. So you want to say there is sufficient evidence to support the massage therapist program that can reduce the percentage of migraine headaches from 15.2%. So there is evidence. Does that make sense? Because we're what? We're rejecting the null hypothesis. Okay?
And the no, that, whatever you say.
Null hypothesis.
500?
No, that's the sample. That's the amount of people. The null hypothesis in this case is that P is equal to 0.152.
Oh, okay.
Oh, so if it's equal to 0.152, it stays the same and what you did doesn't matter.
That's right.
But if it is the other way around, what you did matter.
Right.
And it affected it.
Right.
So that's how it says it.
That's why we say the statement. Yes.
There is sufficient evidence.
Right. So in other words, we reject this claim
Because
and support this claim.
yeah, because when the first one you go to therapy, it stays the same.
That's right.
But on the other one, it would be P, what she's doing, minus the stress minus what she does. And that would be that she reduced it, right?
Yeah, she did.
She did.
Right. So this is we don't know what it is. We don't know what it is. It could be something.
In general,
But we know it's smaller.
Any amount, it will be smaller.
It would be smaller than this number. That's right. We don't know exactly what it is, but whatever it is, it's smaller, right?
Yeah, it will be. Yeah. Okay.
Does that make sense? And we're going to figure out how you actually make these ideas of rejecting or not rejecting, how you actually do this in a minute. Okay? We're going to learn, you might say, well, how do we know when to reject or not? Is there a criteria or a reason or some kind of a formula that we need to learn in order for us to do that? And the answer is yes. It's coming up. Really soon to that. Any questions on this? Let's start in there. You got it? Okay. Good. Yeah, okay. You suppose in fact, now here's something again. What if, suppose in fact, percentage of patients in the program who experience migraine headaches is that value? In other words, it's actually goes back to the null hypothesis value. So we rejected the null hypothesis, but the null hypothesis is what? True. What did we do? Type 1 or type 2?
Type 1.
What type of
Yeah, what type of error? So let's see. How many people how many people think this is a type 2 error? Raise their
I
hand.
think it's type 2.
Type 2? Type 2.
I think it's
Type 1.
You think it's type 2?
It's not.
So let me say it. We rejected, sure. We basically, because in fact the percentage of patients in the program who experience migraine headaches is 15.2%.
So we need to reject it now.
Well, so we don't need to reject it, we did reject it.
Oh, we did reject it,
We-
so now we need to find out the error that it is.
Yes, we rejected it. So how many people, hold your thought, how many people say type 2? Raise your hand. None of you. So it's gotta be a type 1.
Yeah.
Because you're rejecting the hypothesis when it's true.
Okay.
Does that make sense?
Reject the null hypothesis.
Now I wonder, you're right. You're right. No, it's okay. That's all right.
I was like, no, the way this is coming across when you read it, it seems my mind is trying to.
You just have to get really used to it. There's a really good table on page, what is that?
432.
On 432 in your book, that actually gives you a chart of what to do. Okay? It tells you when you're committing a type 1 error, when you're committing a type 2 error, and then when you're doing the right thing. So on page 432, yeah?
432.
432. Yep.
Oh, I see.
So this is correct and this is correct. Yes. You're right. Yeah, you're perfect. You're doing great. On page 432 in your book, there's a really good little table.
Gives you the reality and then the conclusion. to
Yes.
reality.
So it really helps you out. And we just finished 10-1. 432. Now, we didn't really, how do you know when to reject or when not to reject? That's what part of 10.2 is about. Okay? And there's two approaches to do this. In other words, there's two ways to really do hypothesis testing. Okay? There's what we call the classical approach. That's one approach. And that's the old way of doing it. And then there's what is called the p-value approach. That's the modern way to do it. And ideally, I'm going to test you on p-value. But I want to show you this too.
You said there's two, there's the classical approach.
And then the p-value approach.
There's the p-value.
And actually, I'll show you what it is in a maybe that slide. So the first approach is the classical. Oops. And that's what we're going to do now. P-values coming up. So notice what we're looking at. Z, right? So Z scores come into play here. Okay? So this is called the Z test, or sometimes called the 1Z test for a proportion. Notice we're hypothesis testing for a proportion. We're not hypothesis testing for a mean right now. We can do it for a mean, but we're doing it first for a proportion. Okay? You feel that? Yeah. You're welcome. I'll try to post this and you can get the rest of this, okay? We'll see you Monday. See you Monday. Now this hypothesis test that we're dealing with, see you on Monday, okay?
What time is the class on Wednesday?
What class? The class you're talking about? 5.
5 o'clock.
Yeah. So a hypothesis test involving a population proportion can be considered like a binomial experiment where you have successes and failures. So we learned that the best point estimate, and this is something that you're going to have to know for your test on Monday, for the population parameter is the sample proportion. P hat, right? Remember that? Remember this? This is something you. This is chapter 8. This is something you have to know, and it pops up here too. You got to know this. And here are the two methods that we can use for testing hypotheses for proportions. The first method we call the classical approach. That basically compares z values. So the classical approach compares z values. That's probably the easiest way I can explain it. Okay?
So we're going to look at a normal distribution?
Definitely. Now, if the sample proportion is too many standard deviations away. In other words, if the sample produces a z-value that's larger than the proportion stated by the null hypothesis, the z-value stated by the null hypothesis, then we reject the null hypothesis. In other words, if your z-value is larger, either more negative or more positive than the hypothesized z-value, then you reject the null hypothesis. And that'll make sense, even more sense in a minute. There's a little more diagrams that are coming up that'll be a little clearer. If the z-value from the sample is larger than the z-value associated with the null hypothesis value, you reject the null hypothesis. Otherwise, you don't.
Is larger or less than
Larger or more negative than the hypothesized z-value. Then we reject the null hypothesis. Okay.
I think it's dying.
Yeah, I'm going to have to plug it in. It's got 7% left. It's going to die in a minute. It's going to die in a second otherwise.
Professor?
Yeah.
I have to leave at 4:30.
Okay. Well, that's one reason why I'm recording it, by the way. That's one of the reasons. Okay, I'm going to have to move this up. I don't really have a choice. I'm not going to be able to read it otherwise.
You can extend it, no?
Not really. I can take care of it. I got it. You got it? Yeah. Yeah, please don't. Yeah, please. This is, if you were in this is my life. I'm not going to be very happy. Really, really unhappy.
Is that good right there? With
Yeah,
the
it's
screen
perfect.
and everything?
Yeah, that's the best we can do. Thank you. Okay, this is about the best we can do. Okay. So, let's go to the next slide. Now, the second approach is called the p-value approach. In a p-value approach, you basically compares probabilities. Okay? So the p-value approach compares probabilities. Okay? No, it's okay. And if your p-value, if your probability of your sample is smaller than your probability of your hypothesized value, you reject the null hypothesis. So in other words, if your probability of your sample proportion is bigger, more extreme means, if your probability of your sample proportion is more extreme. Another way of saying more extreme means it's a smaller probability. Then the probability of your null hypothesis, you reject the what? Null hypothesis. So for example, let's say your probability of your sample proportion is 0.1. 0. You follow me? So let's say your probability of your sample proportion, in other words, what's called your p-value, is 0.1.
Okay.
And let's say the probability of your hypothesized value is 20%. Is 0.1 smaller than 0.2?
Yes.
So since 0.1 is smaller than 0.2, then you, what do? You reject it. Then you what? Reject the null hypothesis. Hold on, Mike. But let's say your p-value was, in other words, the value of your sample proportion probability is 0.1, but your value of your null hypothesis is 0.01. Would you reject or not?
You said
If it's more extreme, meaning it's smaller. So let's say let's say your hypothesized value, your sample proportion probability is 10%. But the hypothesized one is 0.1%, 0.0%. You don't reject, because it's too small, right? You don't reject, it's not small. In other words, sorry, let me say that again. If this value is, let's say, 10%, this value, let's say, is 1%, would you reject?
No, because it's less, right?
Right. No, is 10% more than 1%, or is 10% smaller than 1%?
No.
More. So if it's more, you don't reject. If it's less, you do reject. Okay? So kind of a way of saying that. Let me show you a way of saying it in kind of a nice way.
Extreme means small in this case?
Extremes mean smaller.
Oh,
Yes. Yeah, that's a little ambiguous.
Yeah, it is.
I thought extreme.
I know.
Yeah, extreme, most people think
Oh, extreme
extreme.
is rare, right?
Extreme is rare. In other words,
Yeah.
smaller probability.
Yes.
So, in other words, if your p-value,
We're always going to get an hypothesized one, right?
alpha, yes,
Okay.
is smaller than, here's kind of the easy way to remember this. If your p-value is smaller than your level of significance, in other words, the type 1 error, you reject. If your p-value is, and I actually even told you what the p-value is, but you just have to live with it for now. I'll explain what it is in a minute. Actually, Wednesday, sorry. If your p-value is what? Larger than your level of significance, then you don't reject.
You don't reject the null hypothesis. We call that alpha the what?
Level of significance. In other words, the probability of a type 1 error.
Your p-value is larger?
So if it's larger, if your p-value is larger than the type 1 error, probability of a level of significance, you don't reject the null hypothesis. If it's smaller, you do. We're going to really go through this in 10.3, because that's where this technique pops up, okay? But this is something I want you to know. This is how I'm going to ask, I'm definitely going to ask you a question like this on your final. Okay? Got you. Now, in this section, we're going to focus on the what approach? Classical approach is correct. So let's do that. So in this section, I'm sorry, did you need it? No, are you sure? Yeah. In this section, we're going to focus on the classical approach. So you're making me think about investing in one of those whiteboards. I'm thinking about doing it after today.
It's a lot easier.
Yeah, I just have to set it up, I think. Okay, now what this is here, there's 3 conditions that we have to look at in order for us to do hypothesis testing. The first is that our sample has to be random, or simple. In other words, we must do simple random sampling. Or the data result from a randomized experiment. Either the experiment is random, or we sample randomly. Okay? Does that make sense?
Mm-hmm.
Everybody knows what I mean by that? In other words, we're not favoring everybody. We're taking what? We're like numbering, let's say, all the subjects, and we're using a random number generator, and we're just picking them. There's no pattern. Everybody has an equal chance of being picked. The second condition, this one right here, says that the sample size times that's the hypothesized value of the null hypothesis. This is 1 minus the value of the null hypothesis. That product has to be what? Bigger than or equal to 10.
Okay.
This says that P0, that's the hypothesized value. That's the value of the null hypothesis.
The value of the null hypothesis?
Yes. Or we also call the hypothesized value. is another way to say it.
Null hypothesis.
Your daughter behaves very well, by the way. Nice.
Thank
You're very nice, polite young lady. Thank you.
Value of null.
The null hypothesis, yeah.
So the value.
Of the null.
Times the value of the null hypothesis.
Times 1 minus that value. That's the complement.
I'm times 1 minus the value.
Yeah. Notice 1 minus P0 is the complement of P0, isn't it? Because the sum of those two have to equal 1.
In the book, they don't have that on here. They don't have,
The conditions?
they don't have that
P0?
Yeah,
That's what we, I think,
see right here.
they have it as P, so they're calling it P, which isn't really accurate. So we'll call it P0. And then the sample, the values, they're independent of each other. What does that mean? That the probabilities of picking one of them is not affected by the probability of picking the others. Their probabilities don't affect each other. Does that make sense? So that's why they're independent. So those are the first things that you want to do, is look at the conditions and check and verify if those are true.
What is P0?
P0 is a hypothesized value. So for example, in the SAT one that had 516, that would be, well, actually, excuse me, that wouldn't be right. Let's, the 0.152, one that we looked at, proportion, 15.2%, that was P0. Does that make sense? See how it says 0.152?
Yeah.
That's P0. Does that make sense?
What the rest of it?
Example 3, yeah. See where it says the null hypothesis, it says P equals 0.152, that's P0. Make sense? Now, this is kind of what you're getting at. Your first step is to write the null and the, what kind of hypothesis?
Alternative.
An alternative hypothesis. So your first step here, and then we'll go on, is to write the null and the alternative hypothesis. Either it's going to be two-tailed, which means you're not going to have a not equal to on the alternative. It's going to be left-tailed, that means you're going to have a less than. And then it's going to be right-tailed, it's going to be a what? Greater than. And P0 is the assumed value of the population proportion. That's another way of thinking about it. So that's your first step. Is to write your what? Null and So that's the first thing you want to do. Write your hypotheses.
Do you have to write for all of them, like left and right, or two till nine?
No, there's going to be one of those three. Remember?
So it depends on which one you're gonna.
Right. So, like for example, if you remember, we had less than for the massage.
Right.
So it was this one. It couldn't be the other two. And that's determined by the problem. Next, you pick the level of significance. The probability of getting type 1 error. And remember, I'm going to give you that. That'll be the problem. Oops. I think it's worse. Probably both. Excuse me, Des. It's just, I talk all the time. I think what it is I strain my vocal cords. That's what I'm doing. I think that's what I do. I think I strain my vocal cords. Because I teach so much that I don't give my voice a chance to really relax.
They sell these microphones that you can put right here and you can talk to the class.
Really?
Yeah, you can even carry it around with you here.
That might not be a bad thing to do. And broadcast out.
It's pretty loud,
They have that
yeah.
in the biology group, they have
Yeah.
those, and then we could hear it talk.
Well, also, I think it's just, I just talk so much. I think it's just because I just do it, it's using it. I don't think it has to do with volume, I think it has to do with utility. In other words, I just need to shut up. I mean, that's live. I just gotta stop teaching. Yeah. Or at least less. I'm still teaching. I'm going to quit another place though. By the way, that's live too. Now, now you might wonder, how do we get the comparisons? In other words, how do we create the z-values that we're looking at? One thing you need to do is compute what is called a test statistic. And this comes from your sample. So notice what it has. It has p-hat. Remember p-hat? P0 is the null hypothesis value, and n is the sample size. Does that make sense? So usually you're going to know p0, you're going to know n, and you could compute p-hat, or you could figure it out. So basically, you just have to kind of identify what's what. Does that make sense? And then just have the statistic. And then what do you do? Here, let me do it this way. And what do you round this number to? How many decimal places? That would give us a probability you'd be right. It's 2, because it's a what? It's a z-score. So you compute this. And then, what you do is you look up, depending on what your alternative hypothesis is, you take alpha and either leave it alone, that's left-tailed or right-tailed. So alpha is this area, this probability here. Or if you have two-tailed, you take alpha and divide by what? 2. And these little blue regions are called critical regions. That's where if you want to reject the null hypothesis, if your z-value is here, or here, or here, or here. If it's in any of the non-blue areas, you don't reject. And that's the idea. Does that make sense? So in other words, we reject the null hypothesis when our test statistic, z0, is in the blue region here or here. It'll be one or the other if it's two-tailed, right? If it's in here, if it's left-tailed, and if it's in here, if it's what? Right-tailed. Right? So in other words, this means that your z-value is more negative. This is your z-value is more positive. This is your z-value is more negative. This is your z-value is more positive. Does that make sense? Boy, I'm glad I did that on live.
And you said the non-shaded area is
where you don't reject the null hypothesis.
These are C values all of them, right?
Yeah. Yes, they are.
Okay.
Yeah.
The critical region,
Yes.
if we were dealing with numbers, how would I?
Well, this relates to alpha. So you would you would look up alpha divided by 2. Yeah.
Okay, so if you know alpha divided by 2, it's in between those, right?
Right. It's that probability. It's in the body of the z-tail. You're finding the z-score associated with this probability. You're finding the z-score associated with this alpha. You're finding the z-score associated with this alpha.
Yeah. Okay.
And they're all different depending on the situation you have. You okay?
So in between those alpha points that you're saying is where there are the
Critical region.
no, outside the critical regions, in between those critical regions, in the two-tail one.
Okay.
That's the area where you would not reject the null hypothesis.
Right. I was saying it a different way.
And the same over there, and the same over there.
Right. I was saying it a different way. I was saying it actually the other way around. I was saying it, if they're here, or here, or here, you reject. If they're on the non-blue regions, you don't.
Ah,
We would have to find out, of course, all the orders, right?
Well, once you know this because it's the opposite in sign.
Oh, okay.
And then and this is just direct. Once you know this one, you're done. Once you know this one, you're done. You just have to just compare these values to the one you get above.
So you're only rejecting certain regions?
You only reject when your Z value, that statistic that you compute above, Z0, is in those regions. If it isn't, you don't. That's right. And we usually don't, usually we don't teach this way anymore. We're kind of moving away from this because we're talking about p-value. We use a p-value approach. That's the more modern. So we don't do this anymore.
the null hypothesis is not used anymore?
No, the null hypothesis is used, but how we don't compare Z's, we compare probabilities.
Okay.
So it's a little different. But there's a relationship between the two. Do you guys want to know now? Can I tell you now?
Yeah.
Okay. If these values are larger, if your Z value is larger in any of these three cases, then you reject. The other way around, if you're looking at it through a p-value approach, if your areas here are the value you get from Z0, if that probability is smaller than these probabilities, then you reject. So basically, the smaller the probability, the more the chance you're going to what? Reject the null hypothesis. Thanks for coming. See you on Monday. Bye-bye.
Can you say that again? The small?
Yeah, the more extreme, the smaller the p-value. If it's smaller than actually your alpha value or alpha over 2 value, you're going to reject. Otherwise, you won't. And that will make even more sense when we talk about 10-3, which is on Wednesday, okay?
What did you say before? The smaller the probability?
The smaller the probability, the better the chance you're going to reject the null hypothesis. And here's the conclusion that I actually said to you in terms of Z's. So this says that if the number above is less than the Z value here, so that means it's got to be in this region, doesn't it? If this number is smaller than this number, if this Z value is smaller than this Z value, one more time, if this Z value is smaller than this Z value, so in other words, it's in here, or that value, Z0, is in here, we reject. So if it's in the blue region, we reject. That's what it basically says for the first one. Likewise for the second one, if it's in the blue region, we reject. And likewise for the third one, if it's in the blue region, we reject. Otherwise, we do not what? Reject the null hypothesis. What do you think? So basically, you're seeing if your test statistic, your Z0, is larger than the Z value you get from the level of significance. Say that again. What you're doing is you're testing whether your Z0 value, which is called your test statistic, is actually larger, either more negative or more positive than the Z value you get for dividing alpha by 2. That's what it says.
And the alpha?
And the alpha value is. Either alpha or alpha divided by 2. Either way.
And the alpha was the level 1 error.
The type 1 error is correct. And that's usually given in the problem. It's usually stated in the problem.
Smaller than that.
Yeah, so it's smaller than that. So
And
in other words,
one.
right, when you want to reject the hypothesis. So alpha, the type 1 error, produces a Z value. So let me say that again.
Yeah.
Alpha, either alpha divided by 2 or alpha itself, produces a Z value. Why? Because it's a probability. Does that make sense?
It's kind of like the X random variable
Yeah.
gives you a Z value too.
Yes.
Okay, so we're gonna have alpha, based on alpha, we find the z-value, based on z-value, we find the borders, we solve the equation, and we check, right?
Yeah, basically what you do is you figure out what that is, you look at that, you keep that value, you find what Z0 is, you compute, you actually look up either alpha divided by 2, if it's two-tailed, or just plain alpha, and then you decide whether you want to what? Reject, then you compare the Z values. If they're bigger, either more negative or more positive, you reject.
Yeah.
Otherwise, you don't.
So, yeah, the whole problem was the alpha thing and deciding the borders, that's what really confused me for some
Yeah,
reason.
deciding where the borders were at,
Yeah,
me too.
that's what really had me confused.
Okay.
But now that I know that based on alpha, we can find Z.
Right.
Z value.
That's right. That's
Everything
right.
else seems like.
Not too bad,
Yeah,
yeah.
everything else falls in place.
But there's a lot of steps. It's not an easy thing. I'm not saying this is easy. This is
Do you
hard for
still have
students.
to make that curve
Yeah, it's helpful.
to
It's
see
helpful.
where things are at?
I think so.
But you could do it with the numbers too, right? Like just put them on like that. And
Yeah, oh yeah, you could do it that way. Basically, you're saying, is the Z0 value greater than the Z value you get for either dividing alpha by 2 or just taking alpha itself? If it's greater, you reject. Otherwise, if it's either greater or if it's less than, because that means it's negative, then you reject. Otherwise, you don't. Yeah.
A couple seconds ago, you said A or alpha, alpha or alpha divided by 2 is what?
Is the probability associated with the Z value? In other words, it's the Z value for alpha over 2. That's what Z alpha over 2 is, or Z alpha. It's a probability.
So when you reject, I know that you're rejecting that critical region, then you're rejecting the Z, or anything less than whatever the Z
Say that one more
value.
time, please. I'm sorry. Say that one more time. No, it was fast.
When you reject whatever critical region you want to reject.
Well, you're not really rejecting a region,
Well,
you're
it
rejecting
depends on what you get on your Z.
Okay, well, be careful. What are you rejecting? Are you rejecting regions or hypotheses? That's
Hypothesis.
really important.
So the hypothesis that you're going to reject is either going to be one of those tails, right?
Right, so you would reject, so let's say it was two-tailed, you would reject the hypothesis
Right.
if this value is in here or in here.
So we're going to get a value, and that's how we determine which, and then we're comparing it to what? Though?
We're comparing
that zero?
to the value of alpha, in this case divided by 2, which generates a Z value. So basically, what are you doing? You're comparing Z values, aren't you?
And it says it right there.
Yeah, it does, but that's okay.
Sorry.
No, come on. It's symbols, so it's harder. Yeah, you don't know. Let's be sorry. That's okay. That's fine. It's not a problem.
we won't be using this on the test.
I primarily would want to teach p-value, but I want to show you this. In theory, I'm 99% sure that I'm not going to give you a problem like this, but there is a 1% chance. I have to double check it with my, if I can get away with that with my chair. She might say no. I might have to show you this. That's why I'm showing you to you anyway. Otherwise, I'm going to skip this.
Oh.
That's why I'm showing it to you. Because there's a chance that I might give you a problem like this. And you got to know which one's which and which test to use. And actually, on a test, I'll tell you what approach to use. I'll say either use p-value or classical. So I'll tell you in the problem. I think that's fair.
Yeah.
What to use? Yes.
So you can never choose between the two.
You could do. Actually, you could choose. You totally could choose between the two.
And you can get both the same answer?
You would both either reject or not reject. Yes, you would. Yes. What you're comparing is different. P-value is you're comparing probabilities.
Right.
The classical approach you're comparing Z-values. But your answer is going to be the same.
Reject.
Reject or what? Not reject. And either there is evidence or there is not. That was a good
So if you
question.
have a question, if you give us a question and I like this better, I can use this.
Unless I say thou shalt, in the problem, thou shalt use it. So if I say use p-value, you can.
Okay.
Okay? But if I don't say anything, then it's your choice. If there's a thou in there somewhere, then you can't do it. Or use p-value, then you have to do it. Let's do some examples. Okay? And we're going to go over if that's okay with you guys.
That's right.
That's fine with me.
Oh, and the last statement, of course, is what? Write your conclusion.
Conclusion.
There is not,
No,
right?
there is.
Or there is not. This is actually kind of, I'm glad I did this, by the way. I'm glad I recorded this. This was a good experiment. I gotta get in the habit of doing this more often. I think eventually I'm gonna put all my lectures on podcasting. Oh, no, I still have to talk, you know, not really. Because I have to explain things. Because what if people have questions? Because you can explain something, it could be as clear as crystal, and still, I don't know. And you have to help them. You know, you have to help them. I mean, not all of them maybe feel that way, but I do.
You know what, and there's not enough stats tutors in that math lab.
I know.
Oh, goodness.
We've
They
lost
don't like
some.
helping us.
Yeah, they don't.
They will like, oh, we'll find somebody to come to you.
They don't.
Anyway.
Yeah,
There's
I think
only
we lost.
you or that young guy. There's another young guy that.
Josh is really good.
Yeah, I think it's only you two.
No, there's a young lady and another man that
Yeah.
is there.
So young lady, that's really good.
Yeah.
Oh, yeah, Miriam.
Yeah.
Miriam.
Yeah.
Miriam, yeah, she's really good. Yeah, she's really, really good. Yeah, and even then, I volunteered to actually do office hours there.
Right.
Because I don't have to. I can do it anywhere I want. But I'm doing it to help out Maria. And that's what I help out you guys. Yeah, because not everybody can do, yeah, well, there's not enough people who can teach this.
We need a lab. We need a lab that would have a.
Dedicated staff?
Yeah.
If you took the pre-stats, that's all that is.
Yeah, it's a giant
It's a
lab.
giant lab.
It really is, yeah. Yeah, we have a dedicated lab for now.
Can I still take a pre?
You could audit it. You could audit it.
Oh, okay.
Because if you pass this class, which, you know, it's very likely.
I don't know.
No, that's not. If you
That's not
pass,
high probability.
yeah, it's not high probability. Right now you are. So right now you are.
Yeah.
So, you could sit in, yeah, any of you can audit it.
And it's a lot of group work, so.
Yes.
Really?
Yes.
Like pretty much the workbook is group work.
It's practically all group work, yeah.
So you highly recommend it then?
Oh, yeah.
Oh, I'm gonna do that then.
You can sit in, it's gonna be, there are some topics, like Jennifer said, that there are a little different.
Yeah.
I mean, but we basically go through in detail the first five,
Yeah.
the first five, like 4 or 5 chapters of OLI, which is our workbook. I mean, our online book. And we do something, like Jennifer was saying, that we don't do in this class.
Yeah.
We look at, remember we did linear regression?
Yeah.
We don't do that, we don't do linear. I mean, we do linear, we do something else, we do nonlinear. So we look at curves like log curves, exponential curves,
Oh, those
so.
are great.
Yeah.
And then that when you do linear, you do parabola,
Mhm.
Oh,
and you won't see that in this.
No, you won't, not in this class, no. No. Well, because that's the algebra part that you're missing in 125. That's how we give it to you. Does that make sense? Because I'm teaching that class at COC right now. I've been teaching it since 1983. No, 2013. 1983 would be amazing.
When did you start teaching at college level?
2001.
2001.
Mhm.
2 years.
At CSUN. 137.
137.
Yeah, it's going to run from 4:35 to 6:40. But what for you,
It's
it might
3
be.
days, though.
It,
Well, when I took it, it was 3 days, Monday.
yeah,
Wednesday,
it's Monday, it is Monday, Wednesday, Friday. So that's one, and two. Since you're in this class,
Yeah.
they might not. I mean, you could take it, but I don't know.
If they'll audit it.
Yeah, you might want to audit it.
No, I don't think they will. It's really hard to get an audit class here.
Well, what you do is, because how tough it is for me to even have students in here. I mean, I
Yeah.
probably need two rooms. I mean, in theory. But right now, they're trying to pump. The chair right now is pushing people to take the class. So she's like recommending me to go. Oh, Professor Alice is a really good instructor, and you should take this class.
That's how I took your class, because I asked Professor Yoon, who would she suggest, and you were the first one.
Professor Hemingway did that for. Who was my 7th grade teacher. He basically set all the 123. He was my teacher. Seriously, he was my 7th grade algebra
Teach you for
teacher.
that long?
Yes.
Wow.
Well, he was a principal and he worked for the district. He was a pretty high-ranking person in the LA Unified School District. He's up there. We're not really done with this yet. We're really done with examples, okay? Because otherwise it's not going to make much sense. Now, this is a little too bare bones of what I'd probably give you for a problem. Example 2 is kind of more like about what I would give you. So let's look at this. So use the classical approach to test the following hypotheses. So this says, notice it says the null hypothesis says that P is equal to what? 0.25. The alternative is that P is less than 0.25. So it's a left-tailed test. Does that make sense?
Mm-hmm.
You're given the sample size is what? 400. You're given that the number of successes is what? 96. And you're given the alpha level, which is type 1, probability of type 1 error is what? 0.1 or 10%. Does that make sense? Okay.
Gotta remember those formulas.
Remember, the formula.
P pi was,
Well, the p hat, the p hat, I'll give you those.
okay.
So you don't have to worry about memorizing formulas. What they mean, yes, that you do want to know. But memorizing the structure of them, no. I think that's better. So for your step 1, you write your null and what? Alternative hypothesis. Good. And just note that these are what? This is called a left tail test. Good. Very good. This one's good. Oh, this is still red. It is. Next thing we do is we find our level of what? Significance. And that's given to us, right?
Yeah.
Does that make sense? How many you get it so far? Yeah. Eduardo, are you okay?
Yeah.
You okay?
This would equal to a z-score later on, right?
Yes.
Find out
What this is,
right?
yeah, good.
Okay.
We're going to turn this into a z-score. That's exactly what we're going to do.
Divided by 2, and then we can find out.
Well, actually, do we divide by 2 here or no?
No, well, if you can just do because we're doing that later. I was
Yeah.
gonna do like honest and different which one, but yeah, you're right.
No,
So
here you don't want to divide by 2.
only the left.
Only the left. Or if you have right, you don't want to divide by 2.
Okay.
So the level of significance contributes to the Z score.
Yes. That's exactly what it turns into.
Mm-hmm.
And then you want to find p hat. Does that make sense? Does that make sense? I think for the people who missed the class, it's going to be useful. Even for the people who actually attended the first one, it's going to be useful. Because they didn't get this. Yeah, they didn't get the recording. You were in the first one. You didn't get this
Yeah,
first time.
I thought this was really good.
So seeing it a second time helps, huh?
Oh yeah, like I feel like I saw like 20% of what it was, and I was saying.
It's a lot more now, huh?
Yeah.
20%, I see 80%.
80%.
Yeah.
Significance, right?
Yeah.
And then what you do is you plug it into the Z formula, and you calculate that test statistic. And that's its value. It's negative 0.46. Remember you round to what? 2 places? Is that right?
Mhm.
You understand? Okay?
So that's the Z value.
Yeah, that's what we call our test statistic, and that's the Z value for our test statistic. That's technically what we're finding. So that's the Z value for our test statistic. In fact, our test statistic is that value.
And that's what we're trying to solve, right?
No, that's what we need. Because what we're trying to solve, and that's what we're trying to find. And now what we're going to do is we're going to make this 0.1 into a Z value. So we're going to look this up in the table.
The Z table?
Yeah, the Z table. Does everybody understand that? So we're going to look up 0.1000 in our table. Table 5, definitely table 5 is correct. That's absolutely right. Thank you. So this says just that this is a test statistic. That's all it says. So now what you want to do, after you write this, I'll go to the next slide, but I want to make sure, I want to keep this so everybody copies this. Make sure you get this right. I knew I was gonna go a little bit after 5, that's okay. By the way, the thing I was gonna go to was that they're having a wine and food thing over here in the main campus, and that's what it was. All the other professors are there, except for me.
Our work.
Yeah. Yeah, they will have to lift those wine glasses, those are kind of hard.
They're like, where's the
You know, the culinary arts, they do an amazing job with food. So their food, oh my God, their food is amazing.
It is.
It's so good.
It's well recognized.
But you have to get it now.
It's 65.
Like the first semester.
65 for us. Yeah, we're 65 for us. But I would have done that. And then I get to see people I haven't seen in a long time. Like this work.
The experts are on
pretty
there right
soon.
now, right?
That's okay. There's an extra. They're all gonna have
What's the
that.
little red star by the?
That means, just to let you know that's a test statistic. That's just to kind of denote it as a test statistic.
Okay.
To make it different than the one that we're doing with Alpha, okay? Now, this is one professor I haven't seen. She teaches in another school now, and she comes here. And she was disappointed. She thought, I said, well, I got to deal with my students. I'm sorry, they have priority over me. Seriously. Yeah. And so I said, well, I'm sorry. Sure, I'll see you at graduation. We'll go into that. What's that? Now, oh yeah, thank God. So notice where, this is your Z0, your test statistic. Here's your alpha, so this is what you want to look up. The pink value is the critical region. Does that make sense?
Yes.
Okay, so here you want to look up this value in table 5, like Gina told us. And you look that value up. And it's in between, or it's closer to 0.1003 than 0.0985. Does that make sense? So your value is negative 1.28. So, I know. I realize this. You can do it. You complain.
No, it just makes me nervous.
Don't be nervous. You just gotta get used to doing it. Don't be nervous. You can do it. So let's review. What do? You could actually, even anywhere in this problem, you could probably make this a z-value right away, couldn't you?
Yeah.
In other words, you don't have to necessarily do it in the third step. You could find your z-value just immediately from alpha, and you might want to do that.
And it's only if it's left or right, so you can't do 2 because you're divided by 2, right?
Right, so you would have, and then you just look it up.
Gotcha.
And you would just look it up.
Now, when you divide it by 2, do you divide the z value or the
Good question, alpha.
alpha?
So the 0.01, in this case it would be 0.1 you would divide.
You would divide that by 2 and then look up.
And then look it up, yes.
Okay.
And the question is this number smaller than this number? In other words, does this number lie to the left? Does this number, is this in this region or is it not? It isn't.
Larger.
In other words, so if you want to compare them numerically, you want to say, is this number smaller than this number? The answer is no. So you do not reject the null hypothesis. Because in order for you to do that, your value would have to be more negative than negative 1.28.
Right.
So let's say 1.5, negative 1.5. Where would that be? That'd be somewhere over here. Do you see, Jennifer? I mean, it's okay. Remember, this is not class, officially. So let's say this was negative 1.5. Let's say it was. Okay, let's say your star value was negative 1.5. That would be in here, wouldn't it?
Yeah.
So then you would what? Reject. But since this value is larger than this, then you don't reject.
Is it common to use both sides when you divide by 2? Is that rarely happens?
You divide by, when you have a two-sided test, then you would. But it depends on your test. It depends on what your problem says. If you're looking at less or greater, no, you're doing one-sided. If you're doing, let's say, not equal to, then it's 2 sides, then you would divide by 2.
Okay, so it would have to be like P and then be P greater than, or it will be like that, and then you do the sort of.
Yeah.
And it will be the exact same thing, right? Which is divide alpha by 2 and then.
Yes, yes.
Okay, I see.
So, since the Z statistic is not within the critical region, in other words, it's smaller, not smaller, it's larger than your Z of alpha value, what do we do? We fail to reject the null hypothesis, or we do not reject the null hypothesis, same thing. Because we found a Z value that's actually larger, not smaller, than the level significance Z value. Does that make sense? And then the last thing we want to do is write the what? Conclusion. And here you could just say something very simple. There's not enough evidence to support the claim that the p-value is what? Less than 0.25. Yeah?
So for step 4,
Yeah, this says since the test statistic Z0, Z sub 0, is not within the critical region. What does that mean? It's not more negative than Z of alpha. Then you don't reject it.
So basically, you're just ruling things out
Yeah.
along the way.
Yeah. Yes, you are. Yeah.
And you have certain percentages
And Z value, the
of
numbers.
testing that results that you got that are not supporting the evidence.
Yes, yes. Clarify it? Any questions? Okay, Sandra?
It's way better than the first time.
Yeah, probably, I was kind of expecting like having like
Were you here
overflow.
this morning?
Yeah, but I don't know, like, I guess that wasn't really focused because the, I don't
It
know.
was the morning.
It was the morning.
It was 8:30.
It was really early.
Yeah.
I did feel asleep at 3
I was doing my homework.
I want to make sure that I was here.
I appreciate you being here so early.
Yeah.
No problem. No problem. No problem.
Yeah.
Sure. No problem. Tell me when you're ready. I'll-
Okay.
You ready, Jennifer? You're not ready, right?
Oh, yeah.
Okay, here's the last one, okay? This will complete 10-2. And this is something like more along the lines that I've been giving you, okay? No, I can't do this. No, it's black and white test.
It's like a rainbow in the background.
Yeah.
Sun.
I mean, this is just for you. I mean, on the test, it won't be that pretty. It's gonna be black and white, I'm sorry. Well, that's pretty. Well, actually, that's pretty too. Black and white is actually very pretty. The percentage of physicians who are what? Women is what? 27.9%. So right away, you know your hypothesis testing with a P. Because you're given a what? A percentage. Good. Good. Okay. In a survey, now here's a sample. So that's what you want to look for. In a sample, a survey, physicians employed by a large university's health system had that 45 out of what? 120 randomly selected physicians were what? Women. Now notice how it says use the classical approach. That's what I mean. So it's dictating you what to do. So use the classical approach, or I might put it at the very end of the problem, okay? So you use the classical approach to determine whether there is sufficient evidence at the 0.05 level of significance to conclude that the proportion of women's physicians at the university health system exceeds 27.9%. So this is a right-tailed test. Why? Because you're exceeding. That means you're getting a value that's what? Bigger or larger. Good. Does that make sense? Exceeds means larger.
I'm also wondering, use the classical approach to determine whether there's sufficient evidence at the level of significance. I was
Okay.
thinking the level of confidence where it was on the chart. It's not that.
No, it's different. It actually, well, they're related though. This number here, if you subtract this from 1, you get the level of the confidence level. So if you subtract that, the level of significance from 1, you get the confidence level. Isn't that interesting?
That would be easy.
1 minus 0.05 gives you the confidence
It's the
level.
right tail.
Yes.
So you can do that legally.
Yes. Is that interesting?
Yeah.
So our hypotheses are that, what? P is equal to 0.279. Does that make sense? That's your what? Your no or alternative?
No.
That's your no. That's your alternative. What do you think? Okay? I'm gonna do this one. I really like this one. That's a good camera. Next thing is you pick what? You pick alpha, right? You pick alpha. But you know it. Do you agree?
How do you know it again? Oh, because it's significant levels. That's right.
Mm-hmm. That's correct.
So alpha is
0.05 or 5%. And if you want to, you could look this up directly. In other words, if you want to, since you're dealing with a right tail test, you divide this by 2 or no?
No.
No, you don't. So you directly look this up. So if you want to find the z-value right away once you get alpha, you may.
You don't have to go through that whole.
You don't have to
Yeah.
do it at the end, right?
You don't have to do it at the end. You can find it right away. And then you can make your little picture
I'm
right
doing
away.
it right now. It's
You can do it right now. If you want to do it right now, look up 0.0500.
There's a 0505 and a 0495.
So it's in between the two. And they're both what? The same amount? So it's 1.645? I think it's 1.645. It was in between the two.
Yeah.
So this value, the z value corresponding to this, would be 1.645. We did that for confidence intervals for 90%. Remember that?
Oh, that's right. Oh,
Remember that one?
yeah.
We did that for confidence levels. That's why it's 1.645. Did you guys get, I'm sorry, did you get this? There's nothing more to it. Now, you gotta find p hat and you gotta find z. And your value is what, 2.34? Does that make sense? That's just a calculation. That's the test statistic. That is not the level of significance of z value. Do you see the difference?
Say that one.
This is the test statistic. This is not the level of significance of z value.
Oh, okay.
You see the difference?
No.
Okay, the test statistic you compute with p hat and p0, the hypothesized value, and the sample size. That's your test statistic. Okay, the other one, the alpha equals 0.05. That gives you the z value for 5% or 0.05, the level of significance of z value. So they're different because that's what you're comparing. So you compare this with step 2, z value, which you could find out. We found it to be 1.645.
I see it. It's negative to me. Negative
It
1.6.
It might be negative. It probably is, actually. Let's take a look. I think you're right. Actually, no, it can't be negative. You know why?
No.
It's right.
Because it's right tail.
Oh, that's true.
So it can't be negative. So what you do, well, remember how you figure out the z value for this? Subtract this from 1. Do you agree? You get 0.9500. Is that what you did? And then you look it up. Oops, sorry. I'll make sure you guys get this, and then we'll go to the next slide. We're almost done. And then I'm going to tell you guys things to know in the test. Everything. But, yeah, that's
For
it.
Monday or for
For
the
Monday.
final?
For Monday.
Okay.
We won't talk about the final, until the final comes up.
Oh, I
Look it
see.
up on table 5, it's 0.279.
That's interesting. You don't look up that, you look at the level of significance.
Yeah.
So you look up this value.
And you get 2.2, no?
No, you don't. No, you get 1.645. Because remember, what you're going to do, this is right-tailed, so you subtract this from 1, and you look up 0.9500, which is, remember, the area goes this way.
Oh,
So-
I see it now. Okay.
So you subtract this from 1, and you look up the value here to give you the z value, and that's going to be.
Yeah.
I'll show you the slide. I'll show you the slide. I'll just wait till, I just want to make sure everybody copies this, and I'll show you what I mean.
So the z value minus 1?
Yeah, well, the alpha value minus 1, not the z value.
Not the z value, and then
No.
you do the alpha?
And then-
you do the z, right?
So then you find the z from that. So this is going to be, think about it this way. This is 5%. This is 5%, right? 5%? Subtract that from 100. You get what? 95%. You look up 95%.
And that's gonna give you
The z value,
which you're gonna use to compare to that.
which you're going to use
Yeah.
to compare it to 2.34. Yeah.
Okay.
Now, it's in between the numbers, so that's how I got
1.645. Yep. So, this is what I mean. You
Yeah.
subtract from 1. Therefore, you look up 0.95 what? 00.
And that's 2.
And that's in between
There it is.
0.9495 and 0.9505. So that corresponds to 1.645, because in between the two. You see? No?
Yeah.
I see that part. So then that number is,
Well, this is 1.645.
right. And then I'm looking at CO.
You see, this is 1.64, and this is 1.65. This, you're looking at 0.95.
And then we check the 1.645.
Right, we have 1.64 and 1.65, and then you just add, so it's between 1.64 and 1.65, but it's halfway between, so you add and divide by 2.
Right.
So you guys understand how we got 1.645? You add those numbers and divide by 2.
But I'm saying, for CO, it equals 2.4.
Yes. Well, yeah. So what do we, so what do you do? We haven't hit that part yet, we're about to. We haven't hit that part yet. No, you're gonna reject it. You're rejecting it. You're gonna reject it. So let's wait. So does everybody see how you get 1.645?
Yeah.
Clear?
Mm-hmm.
Eduardo?
Yeah.
Okay. Alma? Clear?
Yeah, because when I looked it up, the alpha on here, I got a negative number. And it didn't make sense. Now
Yeah,
this makes more
but
sense.
then by 73 you could just flip the side.
Yeah, I know.
So the question is, that's your boundary. Your boundary is what? 1.645. Your test statistic is Z0. Is that larger than than your boundary?
Yes.
Yeah. Because in other words, it's a bigger number. So you
Reject it.
check the null hypothesis. I think that's what you were trying to do. Basically, we'll look at it this way. Is this number larger than this number?
Yeah.
Yes.
Then you reject.
I don't know why I was thinking the other way around.
What we add and divide by 2?
That's when your alternative is 2k, when you have a not equal to. And we haven't had that yet.
Okay, that makes a lot more sense too. And it kind of brings back the practice on
On confidence levels.
Yeah, on chapter 9 and 8. We go over that.
And then what do you definitely? And then what do? You
There
state
is
your
significant-
conclusion,
Yeah,
right?
Yeah. And it's a proportion, so the other one was not a proportion. It was significant evidence that shows something. I don't even remember the wording, but this is a proportion.
Yeah, both. I think both were
Proportion.
proportions actually. So you would express your answers in terms of percents. So this is the part. I'll keep this up. because this is, next is Chem 3.
Yeah.
So just to tell you what's going to be on the test, you can say if you want.
Okay, well, I'm gonna get this.
Yeah. See, they got that.
Okay, my notes. You gave us a,
2 reviews
you gave us the reviews.
and the answers. You
Right.
should have the answers too.
Yeah, I got all that.
Okay?
Is that what you're gonna go through, or?
No, actually, I'm going to take more, I'm going to be very, very specific. Uh-huh. So you're going to have 11 questions, number 1. Okay, 11 questions. Okay? You should know, remember how you determine whether a population is normal from 7.3?
Yes.
We have those 3 lines and the dots, if they're outside the dot, if the dots are outside those outside lines, they're not normal. If they're inside, they are. You're going to have a bunch of problems that you just have to tell me if it's normal or not.
The ones with the little curvy and
Yes.
the line went like that,
Yes.
little dots.
The little dots in between that we did in 7.3.
Now, let me just clarify, if one of those dots was on the line, did we finally clarify?
That's okay, then it's acceptable.
okay.
It's still normal.
It's still.
It's got to be completely outside of it.
And that's called again the normal.
Normal probability plot. Normal probability plot. So if all your observations are either on or in between those 2 boundary lines, your distribution is normal. Otherwise, it's not normal. If you just have one point that's outside of it, it's not normal. You should know how to do. Go ahead and write that. I'll say what you need to know to do. Remember confidence intervals, 9.1 and 9.2? You should be able to find confidence intervals for the mean and confidence intervals for the population proportion. You should need to find confidence interval for the mean. Remember that would be a t-value. Remember that? We'd use t. And then confidence intervals for the proportions, we'd use z for our critical values. Yes.
Are you going to give us the ones that are on the side of the zeta? Probably like 95 and 90, the ones that are...
I might give you that, or I might actually give you one where you actually have to find the critical value that's not a nice one.
Nice one.
Yeah, you got to figure that out. So I'll ask you to find critical values in either t or z, in addition to confidence intervals. Yes, critical values. That's either z of alpha over 2 or t of alpha over 2.
Say that again.
So you find t of alpha over 2, critical value of t, z of alpha over 2, critical value of z.
Oh,
Okay? You should know how to use the central limit theorem. Remember, if you have a sample and sample means, you're going to do the z-score and find that probability. That's 8.2 and 8.1. You're either doing it with proportions or you're doing it with means.
If you have
know how to use the what?
So let me be here. I'm going to be very specific. Here.
It's the central theorem.
Central limit theorem. That's really important. Almost to the point that we want you to tell me what it is on a test. Let's see here. Okay, so if you remember for 8.1.
Oh, the one where all the means, the sample equals to the mean of the top, right?
Right. So remember when we did, we had problems like this. Let me find one. The IQ of XX of humans is approximately normally distributed with a mean of 100 and a standard deviation of 15. Compute the probability that the simple random sample of size n results in a sample mean greater than 110. So remember, now you're comparing sample means to the pop mean. That's 8.1. So problems similar to that, and that relates to the central limit theorem.
Comparing sample
Means to means.
To regular means?
To pop means.
To pop means, okay, population.
Population means. And then you're going to do the same thing where you're comparing sample proportions to population proportions. That's 8.2. Sample proportions to population proportions. That's 8.2. And you're calculating probabilities for that. And then 7.2 and 3, well, excuse me, 7.1 and 7.2 relate to finding probabilities for single random variables, so either for a proportion or for a mean. So they're like when you're comparing, instead of comparing sample means, you're comparing what? You're comparing individual values to the pop mean. That's your test. There's 11 problems to pop means. Pop mean, actually, singular.
And probabilities for popping?
Pop mean. Question? Question?
Oh, but, I'm by the A, B, and C, right?
Some of them might, and some of them might be easier than others. I can ask you questions about what, if you have a confidence interval that's 90%, and then one that's 95%, or vice versa, is it narrower or wider? So the bigger the probability, the wider it is, but the more imprecise it is. So I might ask you a question about width of a confidence interval.
Well, so far my confidence level is pretty low, so I'm still working.
Okay, so that would be very wide or very narrow? Would that be very wide or very narrow?
I think it's very narrow.
Okay. Well, I like it to be wider. But then you're not as precise.
Yeah.
Okay. Anything else? So look over your reviews. Make sure you can do all the problems on the review.
On the review.
Up to problem number 10 in chapter 9 through 10.
If we do all of those and we understand the concept,
It'll help. You should do okay. Yeah, you should. Okay. That's it. You're welcome. Stop the video. You're welcome.